Hi, my name is Jeremy Swanson. I'm a certified crop advisor for Agronomy RX. Today we're going to talk about nitrogen products, forms of nitrogen, and the conversion processes that happen to make nitrogen available. We've reached that point in the growing season where we're getting a lot of questions about whether farmers have enough nitrogen in their fields to fill out the corn crop. This particular year we've been very dry, and so we really don't have any concerns about leaching. Really don't have a lot for concerns about volatilization, at least for the anhydrous that was put in the ground. And so as we look at our last opportunity here to give nitrogen to this crop, mostly through a wide drop type scenario, maybe some top dressing still going on. But I want to just talk about the different forms of nitrogen and those processes and how we can best manage that here through the rest of the season. So first, let's just kind of go through the basic forms of nitrogen and that we're familiar with or most common in our area. And we'll start with urea. Urea is one that's not used a whole lot in our area, but the chemical compound for that is the CONH2. So carbon, oxygen, and two nitrogen, hydrogen molecules. That form of nitrogen in that particular chemical format is not plant available. It needs to go through a conversion process to become plant available. It is also not overly stable. Although there's a carbon molecule at the center of it, it's easily broken down, and as those components break down, they can be lost into the air as gas. The next form is ammonia. This one we're pretty familiar with is NH3. It is not plant available in the NH3 form. It needs to go through a conversion process, and as most of us know, it is not stable as well. Ammonium, NH4. This is a plant available form of nitrogen and it is very stable in the soil. Due to it having a positive electrical charge, the soil, which has a negative electrical charge, is able to hold it. So as we convert and get nitrogen into the ammonium form, the soil is able to hold it, we're able to make it last longer until the roots and plant are able to take it up. The next form is nitrite. We're not going to spend a lot of time on this. It's really not taken into account in any sort of calculations for nitrogen. It's kind of an intermediate step as ammonium converts to nitrate. And it's not in the nitrite form very long, and hence we don't give it a lot of credit. It is plant available, however, it is not very stable. It can be broken down if it is not converted into nitrate very quickly. And then nitrate is the form of nitrogen that we talk about a lot in terms of losing it or in leaching down through the soil profile with water. This is plant available, and again, it is not very stable as well due to the fact that it can leach and move very easily with water. The one thing that I think gets overlooked a lot with nitrate is quite often in overly saturated soils, yes, we can lose some nitrate down through the profile, but quite often a lot of the nitrate actually gets lost to denitrification and lost into the air, more so than what goes into down through the soil profile. So now let's look at, now we got the forms of nitrogen and understanding of what's plant available and what's not. Let's look at that in terms of products that we can use to apply nitrogen to our field. So dry urea, that is the same as the nitrogen form, the molecule is the same. Anhydrous, again, that one's the same in the NH3 form. And then there's UAN 32%. This one I think is very interesting because we overlook this a lot in terms of what makes up 32%. We get stuck on just simply looking at the amount of available nitrogen that we can get out of it and apply accordingly. But we need to take a step back and remember that UAN stands for urea, ammonium, and nitrate. There's 3 different forms of N in that product. And then we want to stop and look at the ratios of each of those products that are in it. The urea makes up 50% of the total nitrogen in UAN 32. Ammonium makes up 25%, and nitrate makes up the other 25%. So as we get talking about nitrogen stabilization products here in a minute and the conversion processes that happen with the different forms of nitrogen, keep this in mind, especially with the stabilizers, because most of the nitrogen stabilizers are really only going to affect that ammonium ion in that 25% of the nitrogen. There are some stabilizers that affect the urea, and we will talk about that in a minute. But most of the stabilizers, at least for 32%, are going to be focused around the ammonium. So stabilization. Urease enzyme inhibitors. So the urease enzyme is what works on the urea molecule and can break it down to the point where it can be lost into the atmosphere. So that type of stabilizer will prevent those enzymes from feeding and working on the urea molecule to try and keep the urea molecule in its form and keep it stable. One common trade name for that is Agritane. Another nitrogen stabilization tool is the nitrification inhibitors, products like N-Serve and Instinct. They work to protect the ammonium ions from converting to nitrate, because we know that the ammonium ion is stable in the soil and is plant available, and so our goal with those inhibitors is to keep it in the ammonium form. The third one we're going to talk about today is which is what this presentation is really kind of focused on, is kind of a new concept that's coming to the market in terms of managing nitrogen stabilization, and that's carbon-based nitrogen stabilizers. And the product we're going to talk about today is CarbonWorks cetane. One thing to note when we talk about carbon-based products, some people may use the term humic acids interchangeably with the carbon. Generally speaking, they're one and the same. Just make note, if you're looking at humic acids and looking at using them as a nitrogen stabilization piece, make sure you confirm that they are acids. There are a number of humic acids in the marketplace that actually have a pH of close to 9, even 10 at times, which is not an acid. So beware of that, and also ask the question if it has oxygen attached to it, which we'll talk about all that more here in a minute. So now we're going to get into chemistry class. Now hold with me, we aren't going to be in this very long, but I think this gives a nice visual of what's going on as we look at the urea conversion process. So you can see the chemical name for the urea compound listed there on the top, right here. And then we have a picture of what this looks like broken out. So we have our 2 hydrogen molecules attached to a nitrogen, 2 more hydrogen molecules attached to a nitrogen, both of which are attached to the carbon at the center and an oxygen molecule off to the side. So what happens when ammonia breaks down, or when urea breaks down and converts into the plant available form? Generally speaking, it reacts with water, and there is an additional step in this process, but it really brings no significance to what we're discussing today. And so I left that out to try to simplify things as much as possible, because it gets to the same result. So urea reacts with water, and what happens is when those molecules get intertwined, we end up with 2 ammonia particles. You can see the hydrogens move over, And everything has to be balanced, and so that then leaves us with carbon dioxide, which can be lost into the air. Real quick, looking at urea stabilization processes, those urease enzyme inhibitors protect this molecule from being broke down by those enzymes. However, once it starts reacting with water, that process is going to happen and it is going to convert to NH3. Now, what did we talk about a minute ago in terms of NH3? First of all, it's not plant available, and second of all, it's extremely unstable. It can be broke down and lost off into the air as gas as well. So we need to convert that. So now the ammonia conversion process. What we need here is a hydrogen ion, because the extra hydrogen ion to this molecule now makes it NH4 ammonium, and we know that to be a stable compound. So we need hydrogen. Well, that's pretty easy in a lot of soils. Think about pH of your soil for a minute. Any soil pH below 7.0 is going to have available hydrogen. Okay, it is acidic, indicating hydrogen. Now, a pH of 6.9 is not going to have as much available hydrogen as a pH of 5.0. Now, just so nobody goes off the deep end with this, I'm not saying that we should all have pHs of 5.0 so that we have ample hydrogen to convert our ammonia. I'm just saying is that we need to be aware of our fields and the pH of our fields to understand when we're dealing with the ammonia conversion process how much hydrogen is available to get that job done. And if we look at pHs above 7.0, that indicates a lack of hydrogen in the soil and could be a problem in terms of converting this ammonia into ammonium. So how are we going to get around that, especially in the cases of high pH soils? How are we going to stabilize the ammonia? Where's the hydrogen going to come from? And this is where I'm going to start to address the product of cetane and how it helps stabilize urea, or in essence, ammonia here. Cetane has a carbon molecule at the center and molecular hydrogen attached to it as well. So the idea being, as we add cetane to urea, and urea starts through this process of converting, once it hits the ammonium form, there is a hydrogen available, even if it's still in the tank, has not even been applied to the field, there's now a hydrogen ion in there to help to convert it into the ammonium form for us. So now that we've got it in the ammonium form, let's talk about converting the ammonium form all the way through. This now becomes a biological process, and many of us are familiar with this. Nitrosomonas bacteria in the soil are what feed on the ammonium and convert it into nitrite. Again, this is a bacteria process. Living organism does this, not a chemical process. As we talked about, nitrite is plant available but incredibly unstable, and this whole process happens very quickly. So then there are nitrobacter bacteria in the soil that will feed on the nitrite, and that is where it gets converted into nitrate. So now that we've seen the conversion process all the way through, let's go back to our stabilizers for a minute. We know that the nitrification inhibitors protect the ammonium ion by putting the Nitrosomonas bacteria to sleep, rendering them inactive from doing their job, which allows the ammonium ion to stay in its chemical form. Now, I'm not a big fan of limiting the biology in the soil and putting them to sleep. So how do we get around that process? Well, this is where cetane comes into play again. So we've used those hydrogen ions off of that carbon molecule to stabilize the ammonia. That now leaves oxygen. So oxygen, as you can see here, we're moving from hydrogen ions to oxygen ions, and I said it's not a chemical process. So in reality, what these oxygen ions do is bolster aerobic bacteria. Okay, it bolsters biology. There's anaerobic and aerobic bacteria in the soil. The oxygen helps bolster aerobic bacteria. This is a major thing in wet years when we have extremely saturated soils and there's very little oxygen available in those top few inches of soil to help this process. So by introducing oxygen with the nitrogen that we're applying, we can now help bolster biological activity. Now, it does help bolster the process of converting the ammonium over to nitrate, but here's the clicker. Here's the thing that really makes it all tick. Once we've used those oxygen molecules off and we have it in nitrate form, there's probably still some ammonium form in the soil, that leaves that pure carbon molecule in the center, which is what we're going to talk about next, and its ability to hold nutrients such as ammonium and nitrate. But before we get into how the carbon does it, let's look at our soil CEC for a minute. Cation exchange. This is a value that we get on our soil tests, and so we have some idea of the soil's holding capacity. Okay. Typically, these are always electrical charges. In rare cases, we will see a positive charge, but due to the low number of sites or exchange sites in our soil, there are very few positively charged sites, so we don't even give any credit to it. What drives CEC? There's two things, clay and organic matter. So the more clay you have in the soil, the more organic matter in the soil that you have, the higher your CEC values will probably be. It also depends a bit on the type of clay. Average values for CECs in our soils in Iowa will be somewhere between 15 and 40. Sometimes they can be less than that. Not very often do we see it over 40. So let's put this in perspective. CEC gives us, like I said, gives us an indicator of the soil's ability to hold things. The old rule of thumb is if you take your CEC value times 10, that will equal the amount of ammonium N the soil can hold. So if we have a CEC of 20 and we take it times 10, that's 200. That would tell us that we could hold 200 pounds of ammonium N. It does not mean that we can hold 200 pounds of nitrate. It does not mean that we can hold 200 pounds of urea. It only means that we can hold 200 pounds of ammonium N in a 20 CEC soil. So our soil is limited in its ability to hold things. Just so we're all on the same page as we talk about negative and positively charged ions for a minute, let's think about a magnet. And a magnet has a positive and negative end, and when you put the positive and negatives together, they attract. And when you put two positive ends together, they push each other apart. You cannot push them together. Same thing if you put two negative ends together, they will repel each other. So the same principle applies as we're looking at things like ammonium and being positively charged. As I mentioned, our soil has negative charges to it. So when you have a negative electrical charge on the soil, positive on the ammonium ion can attach to it. So now let's look at carbon. Pure activated carbon. And there's very few of these out there yet. But pure carbon has a cation exchange capacity as well, and is significantly higher than our soil. Pure carbon could have as much as 700 or higher exchange sites on it. And when we take and increase the amount of sites by that much, it then allows us to have some positively charged sites on it as well. So now that we have some positively charged sites, we now have the ability to hold nitrate, which is a negatively charged ion. So now you can see how pure carbon has the ability to hold both ammonium and nitrate because it has both positive and electrical charges to it. Quick review of those with their charges next to them. Ammonium has the positive, nitrate has the negative. Carbon from our soil, coming from organic matter or CEC from the clay, have negative charges only. And pure activated carbon has both positive and negative charges to it. So to wrap this up, thinking back to the urea compound, in both dry urea that can be top dressed or the urea component of UAN32, there's a tremendous amount of nitrogen there that ultimately may go unstabilized, that we don't even think about with UAN 32%. 50% of the nitrogen in 32% is in the urea form. It needs to go through a couple of conversion processes. Carbon becomes a very effective tool to help manage that, especially with the hydrogen and oxygen ions attached to it, like it is in CarbonWorks cetane. Plus, when all those things are used up, when the hydrogen and oxygen is used up and the plant uses up the ammonium or nitrate that's attached to the carbon that's left is food grade carbon for the biology in the soil. So now we can feed the biology with what's left behind. So now we've stimulated biology and promoted soil health in the process without rendering biology inactive, or in maybe some cases even killing biology off. We're going to stimulate the entire system. So I hope this has been helpful in understanding the different forms of nitrogen and some of the different stabilization processes and conversion processes that go on. If you have any further questions, check out agronomyrx.com or check us out on Facebook, and we'll get in touch with us and we'll help you out if we can. Have a good day. Thank you.